Now, in quantum mechanics, special relativity works in quantum mechanics beautifully. And in quantum field theory, the modes, the ways that we mathematically define the fields and how they change and evolve and interact is described in 3 dimensions of space, 1 dimension of time, in what's called a relativistic manner. Those relativistic effects, length, contraction, time dilation, these are taken into effect in the mathematics of describing this. General relativity looked at quantum mechanics and said, no, fuck you. I don't want to go out with you. We're not working together. The largest thing we've ever been capable of observing is just called the cosmic web.
Yeah.
And that would have a diameter of about 93 billion with a B light years. Now, just for some perspective, 1 light year is just under 6 trillion miles. Just 1 light year. And that's the observable universe. The part that we've been able to see, the diameter of it is 96 billion light years. I'm not even going to attempt to figure out the order of magnitude of miles that is, because it's absolutely insane. There are people out there like William and Craig who think that Einstein's relativity is wrong. And hey, look, if you want to think that the foundation of modern physics is wrong, I will wait to read your published work. Right. That's all I can say.
Welcome back to the Gnostic Informant, and you are about to attain true Gnosis. And I'm joined by Leophilius. And your channel, man, I've been subscribed for a little while now, and you're underrated. I got to say that. You're highly underrated. You are a very smart guy, very well articulate, and you have a good way of explaining things that is easy to understand. Like, I don't have to pick up a book on quantum physics and try to like find all these terms and definitions. I could just go to your channel and get a quick little rundown, and it's pretty nice. Thank you for that.
Yeah, I appreciate that. One of my goals when I started my channel was, there's a lot of, and I like a lot of these channels, you know, the Science Asylum, Parth G, PBS Space Time. They do a lot of really good content, but sometimes they use technical jargon without really explicating it, or they don't explicate it in a way that, at least in my opinion, I think a layperson or people that don't have that technical understanding, they're not going to walk away with the proper idea of what it is that's trying to be explicated. So my goal when I started my channel about 1.5 years ago, roughly, was to do my best to explain a lot of these, what I would consider to be rather complex issues in science, more specifically physics. That's usually what I focus on, is quantum mechanics, astrophysics, cosmology, and even a little bit in philosophy, in a way that I think is going to be palatable for a lay audience, but that still retains a lot of those nuances and technicalities that a lot of other communicators tend to overlook in trying to simplify the concept. Just to give a brief example of that, you'll oftentimes hear in quantum mechanics that, oh, well, quantum mechanics tells us a particle can be in 2 places at once. No, it's never said that. Never said anything like that. What it says is that prior to measuring the position of any particle, there is a probability, however large or small, that we can assign to any potential position it could be in. But we don't know which one well, it's not that we don't know. It makes no sense to say that it is in any position before you've measured that. And so that is what it says. Not that an electron can be in 2 places at the same time, but that an electron, it doesn't make sense to talk about an electron having a place before you've measured where it's at.
Yeah, I'm glad you brought that up, because that when I was a creationist, that was one of my favorite things to bring up in conversations like this. I'd be like, do you know that in quantum physics, 2 particles can be in 1 place or in 2 different places at the same time? And I completely butchered what it actually means. And how did that happen? How did this misconception come out? Because this is a popular misconception. A lot of people still think that right now.
I think that and not that this was done with intention, because I don't think it was, but I think a lot of the earlier science communicators that talked about this were trying to find a way to explain the concept of what's often referred to as superposition in a way that's not super mathy. And in terms of the math, it's actually not that complex. Anybody with a basic understanding in, like, trigonometry, analytic geometry, pre-calculus, linear algebra, stuff like that would understand it. In the mathematics sense, what is being said is that if you know what a vector is in math, it's an object
Yeah.
that has a length or a magnitude and then a direction. So you could think of the best way I like to explain it is speed. Speed is just one quantity. You're either going fast or you're going slow. So there's a magnitude to that quantity.
Sure.
Now, velocity is speed in a particular direction. It is the direction in which you're moving at that speed, the direction that the magnitude, whatever the magnitude is of, is being expressed in. So now there's two quantities there. That is what we call a vector quantity. So observables, as they're called in quantum mechanics, like, say, position or momentum, are mapped as vectors in a coordinate space. And if you think about that, if you it's imagine when you map up a point in a coordinate space, there's a component along the x-axis and a component up the y-axis to get to that point, your x, y coordinates. So when we talk about something existing in a superposition, what we're really saying is that that object mapped in a coordinate space has some component along each of the axes. Now, each of the axes represents an actual state. So the term that is used is a linear combination, which is like saying if you have, like, in a three-dimensional coordinate space, you'd have an x, y, and z component.
Sure.
With a vector, it's the same thing. There's some number along each of the axes that together define that vector we're using to describe the state. And what we would say then is that state vector, as it's called, is a combination of some number along each of the axes. It's a linear combination of those axes. The axes are often referred to as basis states, since they represent, so you'd have your y-axis going up. If the vector was perfectly aligned with the y-axis, then you would say that the electron is in that position. If it was just slightly off the x-axis, then it would have a number along or off the y-axis, then it would start to have a number along the x-axis and the y-axis. So now it's in a superposition of being along the y-axis and now along the x-axis. So that's really what superposition means. And I think that scientists not wanting to spend the time to explain that to a lay audience that might not be up to speed with some of that lingo, we're just looking for a way to explicate the idea of superposition. It's kind of like an electron being in two places at once. Even though I personally here, and I'm not trying to, like, bash on the scientists, I think that is quite a poor way of putting it. I prefer to just say linear combination and then kind of explain what that is, because people understand a coordinate space. They understand that a point in a coordinate space is a combination of a number along however many axes you have making up that space.
And now for the demonstration with the slit, how does that work where it makes it seem like, oh, we're watching it, it's over here, now we're not watching it? How did that come about?
That started with what's called the double slit experiment, where I think I think originally it was done on photons and then later was done on electrons, but don't quote me on that. I might have that backwards. But we'll just take photons because you can pretty much take any particle and do it, almost any particle, and or any particle, it should work. We take a photon, we have two slits, and then we have a detection screen on the other side. And we send the photons through individually, one at a time. When we're not watching to see which slit they go through, the pattern that we get on the detection screen is it's what's called an interference pattern, where waves can interfere constructively, where the troughs add up to make a bigger trough.
Hmm.
or the peaks add up to make a bigger peak, and then the troughs cancel out to make a deeper trough. So instead of, the difference looking like that, it's going to look a bit steeper.
And
You get an interference pattern.
you're talking about the pattern behind on the wall after it goes through the slit. Okay,
Yes, yes, on the detector screen.
sure.
Well, this would essentially mean that the photon evolved through both slits and interfered with itself. But photons are supposed to be particles, and that's what waves do. So let's look and see what happens. Well, let's actually look and see what's going on here. So we turn on a detector, and this sends another photon or an electron or some other particle to interact with that photon just before it goes through one of the two slits. And when we do this, what we get is the kind of pattern we would expect to see if the photons were individually going through one slit or the other. It's kind of like a jumbled mess that you would expect to see if they were just kind of randomly going through one slit. Whoa, okay, so now we're seeing what we want to see here. Seems like everything is good. Okay, we don't need to detect the photon. We take the detector away, we run it again, and the interference pattern returns. Oh, okay, something's not right here. We put the detector back, interference pattern goes away, take the detector away, the interference pattern returns. So essentially, physicists, baffled as they were, eventually arrived at the conclusion that, well, particles aren't really solid bits of something. They're distributions of energy in fundamental fields. And those distributions of energy will evolve through both the slits. The reason why, when we put a detector there, it doesn't do that is because the detector has to shoot a particle at the particle that's going through the slits, which now means that that particle is entangled with the detecting particle, which will change the trajectory of its evolution, getting rid or
Oh,
destroying that interference pattern. So what and Sean Carroll emphasizes this. What the double slit experiment shows us is that this notion of entanglement, that when two systems interact, if you want to describe one of them, it's intrinsically going to give you information about the other system. That this notion of entanglement is much, much more important than we first thought that it was, in terms of how reality behaves and why it can behave in different ways for different observers, measuring the same thing, yet both results be valid.
wow, I have a lot to ask about this. Let's focus on this for a couple minutes. I didn't think we were going to go here, but this is fascinating because this is reality. This is the building blocks of reality. We're talking so small, and correct me if I'm wrong, but isn't the scope of going down to this dimension of reality, isn't it even more like farther? Isn't it even like the I guess I don't know how you call it, distance or scope. Wouldn't it be like farther away than like part of our solar system? Like this is how deep we're in, or is that not true?
In a sense, yes. So if we took a just the simplest atom in the universe, the protium, the first isotope of hydrogen, H1, simplest atom, one proton and one electron. Now, electrons don't literally orbit the nucleus of an atom the way that planets orbit a star, but being a little bit simplistic, we can describe it that way.
Sure.
If we blew that proton up to the size of a basketball, at the ground state, which is the orbital that's closest to the nucleus, the radius of the orbit of that electron would be 7 miles away from that basketball, which means that the total diameter of that ground state orbit around that basketball would be 14 miles, 7 miles in either direction.
And that's you're talking relative in that scope of range of what of like that what do you call it, particle, or what do you how do you describe it, particle?
Well, with an atom, it would largely be described as a system.
Okay, so this system, the scope in this system is now relative, and it would look like you would feel like you're 7 miles away if you were
Yeah,
if you
yeah.
were that size. That's
If you,
so
yeah, essentially, if you could shrink yourself down to that size, and you were the electron in the ground state, its lowest energy state, you could say that you would be about 7 miles away from that proton at any given point.
in relation to our world. That's what I'm saying.
Yes,
Yeah,
yes. When you
that
scale, yeah, when you scale
is
up or scale down, that's yeah.
that is so fascinating because we don't realize that how like enormous this universe is. We look up, we look outward, we look at space, but inward is like even more. I don't know about more, but like it's ginormous.
Hmm. Hmm.
How far down have we gone? Like I'm using like the dumbest way to explain this, far down, but like you know what I mean. Like how deep have we gone compared to how deep we've gone outward? Is there a comparison there, or do you?
So the largest thing we've ever been capable of observing is just called the cosmic web,
Yeah.
and that would have a diameter of about 93 billion with a B light years. Now, just for some perspective, one light year is just under 6 trillion miles. Just one light year.
And
Then
that's
the
the speed.
observable universe, the part that we've been able to see, the diameter of it is 96 billion light years. I'm not even going to attempt to figure out the order of magnitude of miles that is because it's absolutely insane. The smallest that we've ever measured, I want to say, would probably be quantum fields. In terms of the smallest unit of time that we've ever been able to directly measure is referred to as a zeptosecond, and it is a trillionth of a billionth of a second. So that's really small. It would be, bear with me here, 0.00000000000000000000001 of a second. So if
Now,
you could take a second, take a billionth of that second, and then take a trillionth of that, that's a zeptosecond.
wow, that is insane. And theoretically, could you, if you got to that point, could you keep going? Could you cut that in half?
Um, in an ideal sense, mathematically, yes. Whether reality physically can be broken up, well, we are pretty sure that there are times, measurable times, smaller than a zeptosecond. They're at this point theoretical. We haven't really observed them. The smallest unit of time that we think any physics would be applicable within is what's called the Planck time. A lot of people say Planck. The guy was German. His last name is Planck, Max Planck. I'm really pedantic about names. I always have been. It's probably my autistic brain. Anyway, and that is 10 to the negative 43 seconds. If I remember correctly, it's a trillionth of 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 a second, which is really, really things that exist, if they could, for times smaller than that. You might as well just say it doesn't exist.
Yeah, that's just unreal. It's you can't even wrap your head around it. And I'm wondering because you know how people make those like those videos where they shows like the scope of like zooming out and zooming in. I sometimes use them for some of my intros. Um, are any of those accurate? Like, is it like 'cause it seems like when they're zooming in, it's like you're going farther than you are out of space. Like the cosmic radio background, let's say that's the limit of the outside, but then you go all the way in toward and you get to atoms, you get to the zeptons or whatever you're talking about. You get all the way down there. Would that take longer to do that? Or do you think that's not true?
Are you talking about if you could shrink yourself down at a
Yeah, yeah.
constant rate, would it take you longer to get to the
Relativity.
smallest scale than to the largest
Yeah,
scale?
yeah.
Um, for me, that would be a difficult question to answer. I
Yeah.
guess because I guess because we have theories. We've theorized about the largest and the smallest, but I don't think it would be accurate to say that we, as of yet anyway, know what the largest and the smallest is. So, but if we just take the limits that are kind of just there now, I think it would probably be a shorter amount of time to shrink down to the smallest scales at a consistent rate of
Yeah,
shrink
yeah, yeah.
than if you did that same rate getting larger to the largest scales. And I think that one of the reasons for that would be is that we have to remember space-time is expanding. So
Yeah.
that largest scale, in some sense, is continually growing larger. So whereas we don't think the smallest scales are like continuously growing smaller. That's not a thing that I don't think any physicist would say that's something that's happening.
This is just It's just mind blowing just thinking about this stuff. And so, okay, so let's bring it back to what we were talking about before I went off on this like derailment. So what Einstein's where does Einstein's relativity play into all this quantum physics? And because if I'm not mistaken, he sort of opened the door for all this.
In a sense, yes. Einstein, and he didn't do it alone naturally, but he was the one that kind of took the ideas that were there and put them into a singular
Like Aristotle.
theory that sort of gives us a good framework.
Yeah.
And there are people out there like William Lane Craig who think that Einstein's relativity is wrong. And hey, look, if you want to think that the foundation of modern physics is wrong, I will wait to read your published work.
Right.
That's all I can say. But Einstein developed relativity, and it's split into two modes, I guess you could say. In most senses, they are the same theory. It's just the math describing the dynamics is different. And that's special relativity and then general relativity, which came 10 years after he had developed special relativity. And he developed special relativity because people like Albert Einstein, Heinrich Lorentz, Henri Poincaré, who's French, were trying to. We developed electromagnetism. You know, we have the Maxwell-Heaviside equations, and they gave some implications about some things concerning the way reality works that didn't really fit with what physicists were thinking at the time. You know, we thought that light was a wave, or that electromagnetism showed us light is a wave that propagates. Well, light's a wave. Water is a wave that moves through, well, the medium of water. Sound is a wave that moves through the medium of the air. Seismic waves, and these are more than, there's seismic waves on all the planets. There's seismic waves in stars. Those are just the waves that travel through the material of whatever that planet, star, what have you, happens to be made out of. So we know back then, this is what they said. We know that if something's a wave and it's moving, there has to be a medium through which it's traveling. We've got water waves, we got sound, seismic, all that stuff. So there has to be something, some sort of aether, if you will, that light, since it's a wave, must be propagating through. This was called the luminiferous aether. And this is what Heinrich Lorentz and Poincaré and many physicists at the time thought, is that there's some aether there, background aether, through which light moves, and that's why it's a wave. Except that no measurement that we ever did that should have shown this thing was capable of it. Even though, at least at the time, the theories that we had necessitated its existence. And this is where things get a little hairy. Because if you have a scientific theory, a physical model that purports the existence of something, but according to that same model, you won't ever actually be able to observe it, it's effectively unfalsifiable, you have some problems. That's not what you want in your theory. And Einstein came along and said, well, okay, so we know the speed of light is a constant. I'm going to take that as one of my postulates, that the speed of light is constant. I'm also going to take as one of my postulates something known as the principle of relativity. And this was this idea that, and this goes back all the way to Galileo. The idea that, the best way I can put it is, if we were both in a room and I was on one side of a desk and you were standing on the other side and there was a glass of water on it, well, to me, the glass of water is going to be off to my left. But for you, the glass of water is going to be off to your right. So there's a relativity to nature, with things in space, And that, like I said, that was known as the principle of relativity. And Einstein realized, okay, well, to rescue this idea of the luminiferous ether, one of these things would have to be false. Either that the relativity is a thing, or that the speed of light is constant. Well, we don't have reason to doubt those. So let me take those as my two postulates. Let me take some math that the Heinrich Lorentz developed. They were known as the Lorentz transformations, and they're just a way of describing how things can change in space-time that are different from what are known as the Galilean transformations that, well, quite frankly, don't work in electromagnetism. And so what he did is he defined the interval between two events in space-time, which would be the space or time that separates those events. So if it's a separation between two events in space, that interval is what we would call length. If it's separation in time, then that interval was what we would call the time between the two events, the time that has elapsed. And so he used the Lorentz transformations to define intervals between events in space-time, assumed those two postulates, and showed that some funny things happen to objects in space-time when they start moving very close to the speed of light. If I took a ruler or just a pen and I started accelerating it right here, getting close to the speed of light, and I was able to sort of take a snapshot of it when it was sitting right here, this pen would actually look a lot shorter than it actually is. The clock associated with the pen would have elapsed a shorter amount of time once we pause it than what we would have measured just sitting here. So what Einstein was able to show is that when objects begin to move very close to the speed of light, their lengths contract and their time dilates. Now, dilate, people think of getting longer. It's that the interval between the 2 points in space-time gets shorter in both space and time. Now, if the time between two events is getting shorter, what that would mean is that it feels like the time is moving more slowly, which is where we get time dilation rather than temporal contraction. That's why they use that word. And that's essentially gave rise to special relativity. Hermann Minkowski came along and was able to take space, the three dimensions of space and time, and mathematically combine them into a unified diagram, or I should say coordinate space that we use in diagrams, called a Minkowski space, or what we now know as space-time. And this is in a Minkowski diagram, parallel lines will stay parallel. So all lines along the y-axis, you can do this with any of them, and they'll all stay parallel. They'll all move with each other. Same for the x-axis. If you move those, they all stay parallel. Linear is what they would call it. It is a linear coordinate space, I believe. This is the special instance, because space, as anybody that understands gravity knows, is not generally like that. And this is where Einstein started to develop the general theory of relativity. Taking that notion he developed with special relativity that's only true in special instances where we can treat space-time like flat, and generalizing it to the way space-time actually is in most of the universe, where it's curved. So the special relativity and general relativity are, in most senses, the same theory described on two different manifolds. Minkowski space-time versus in special relativity versus, I believe it's a pseudo-Riemannian manifold in general relativity. And that forms the basis of modern physics. Now, in quantum mechanics, special relativity works in quantum mechanics beautifully. And in quantum field theory, the mathematics, I think they're called the modes, the ways that we mathematically define the fields and how they change and evolve and interact, is described in 3 dimensions of space, 1 dimension of time, in what's called a relativistic manner. Those relativistic effects, length, contraction, time dilation, these are taken into effect in the mathematics of describing this. General relativity looked at quantum mechanics and said, no, fuck you. I don't want to go out with you. We're not working together. And physicists have been struggling ever since to get them to cooperate, and they just don't want to. And this is where the field of quantum gravity has arisen.
Is that because the general relativity, you can't scale it down there? It doesn't scale?
It's more that what are often referred to as the field equations of general relativity don't like the mathematical structure of quantum mechanics with this making quantities discrete. So it's either a 1, a 2, a 3, or a 4. You can't have a 1.6 or a 3.4 or a 2.3. It's integers. It's only in discrete steps with nothing in between. The equations of general relativity don't like being mathematically described that way, because essentially what we get is this notion of there being a superposition for the curvature in space-time, which doesn't seem to be a really coherent concept. And so physicists are sitting here scratching their heads going, how the hell are we going to get these two theories to work? And what it means is not, aha, it's something science can't answer, so it must be some sort of like magic stuff or something like that, or a god. It's more that we as humans are still quite primitive and we don't understand everything yet. And we need better tools to make better observations, to better describe how gravity works at the scale, if it even does. Because if space time is emergent, then gravity is emergent, and then general relativity, at least in the ways that we understand it now, doesn't really make much sense on that scale. We'd have to refine those equations and give them a more of a quantum mechanical or a quantum field theoretical description. Many have tried. Pretty much every attempt has failed. Yes, that includes string theory, which everybody seems to think is really cool. And sure, it's cool, but it's almost entirely wrong. And so physicists are just right now they're working on trying to get a better description of the fundamental nature of reality.
And then so E equals mc squared is energy equals mass
Math,
times speed of light squared.
yes.
Wow, and that's such a simple, like most of these equations are like gigantic, and he has this just three letters and a squared, and like how that's just so profound.
Yes, but the thing is, we have to remember E equals mc squared is actually a simplified version of a not really complex but
Oh,
slightly large equation, which is E squared minus PC squared equals mc squared squared, where E equals energy, P is, I believe, momentum, M is mass, and C is the speed of light.
yeah, because
And
you have to get the mass and the speed of light and all that stuff.
Mhm.
That's
And the
just
reason that so for instance, E equals mc squared wouldn't work for a photon or a gluon because these particles don't have mass. But if the energy is mass times the speed of light, mass times velocity, and the velocity is just given as the speed of light, um, how do you get the energy of a photon? It doesn't have mass. Well, that's because E equals mc squared works for anything possessing what's known as invariant mass or rest mass. What this means is that if the thing has mass in an inertial frame of reference, which is a frame of reference that can be treated as one that isn't moving, one that is undergoing no motion. So that either means that it isn't actually moving or it's moving with constant velocity, which means that there is no change in it, it's not speeding up or slowing down. And that would also be inertial. You could treat that frame of reference as if it's stationary. If something has mass in an inertial frame of reference, inertial mass or rest mass, then you can use E equals mc squared. If not, I think for a photon, you would use E equals pc. The energy is equal to its momentum times the speed of light.
okay. And there's a couple other things I want to touch on before I get to Christianity. So I want to just because this is fascinating. This quantum mechanics is fascinating. Um, I'm trying to think which one I want to do first. So okay, let's do Schrodinger's cat. Now, I'm from what I've recently found out about this is actually a misunderstanding of what Schrodinger was actually trying to say. Can you explain
Yes.
that?
Yeah, so Erwin Schrödinger was essentially trying to show that, well, quantum mechanics has to be false because it's absurd. How could a cat be both alive and dead simultaneously? It's just logically incoherent. But if quantum mechanics is true, then that's what it's telling us. Because look, I could take a radioactive atom. There's some potential that it will decay at some time, and then there's some potential that it won't. That's governed by quantum mechanics. And assuming that it does decay, it will, trigger a hammer through some, fanciful hardware and technology that breaks open a vial of poison that kills the cat. So what this would mean is that before we've opened the box, the cat would technically be alive and dead at the same time. What? How does that work? How do you get something like that? And the problem there was that they didn't really take entanglement into account, or what is often referred to. And this whole notion is kind of iffy amongst physicists because where it is and how much it can be stretched is kind of up in the air. But it's referred to as the Heisenberg cut, and it's that not really line, but more of a really wiggly, malleable gray area between the quantum and the classical. And so he was taking concepts at the quantum and trying to apply them to the classical, where they don't have much meaning. We can just make things way more simple. We don't have to really use quantum mechanics. But he was also ignoring entanglement. And this is where Sean Carroll would say there is a world where the cat is dead and you observe it being dead, and there is a world where the cat is alive and you observe it being alive. And both those worlds exist. And this is where the many worlds, and by worlds, this isn't like a completely different, separate universe. It's one universe, but there's different world. I don't. Timelines, I guess you could say, in this one universe that evolve differently as different outcomes, I guess, are realized. And what we observe as wave function collapse is just the splitting of these timelines. And so, what somebody like Sean Carroll would say is that, well, Schrodinger just didn't consider entanglement in his scenario.
Wow. And so it's, how did that go from him trying to disprove quantum mechanics to people actually using this as like a some sort of like example of proving it?
I think that using Schrodinger's cat was sort of co-opted to sort of show the weirdness, as it's
Okay.
often called, of quantum mechanics. That this idea of something being in one state in an entirely contrary state, I'll just use that word, at the same time, which, again, quantum mechanics doesn't really say that. It says that one single observable will be written as a combination of basis states. So there will be some percentage making up the 100% of that state. You might have 40% in this state, 20% in this state, 20% in this state, and then 20% in this state for a total of 100%. So it's not in any state. It's not in no state at all. It's kind of there, but not like
Right.
where. And this is where it gets weird. And
No, it does. But I get what you're saying now. I do. That makes you made it more clear, I think. I want so you mentioned entanglement.
Mhm.
I heard this term quantum entanglement, where it talks about how two different particles can be in two different parts of space time at the same time, but they are dependent on each other, and they when one moves left, the other one moves left or right or whatever it is. Can you
So
explain that?
yeah, what entanglement is telling us is that if we have, so I use somewhat of an example. It's not perfect because I'm talking about classical objects in this example, but I think it does help make the point. Let's say you have two baseballs. They're traveling through space and they hit each other and go off in directions that would be opposite one another. And they start traveling, and then all of a sudden they're billions of light years apart. Well, you see one of those baseballs, doesn't matter which one, you see one of them go past you. You see which direction it's going past you in. Aha, you say, I know which direction the other one is moving. But you're measuring this baseball to figure out which direction it's going in didn't have a physical effect on the other ball. It's just that since they're moving in opposite directions without ever observing the other one at all, if you know which direction one is moving in, then you know the other one is moving in the opposite direction. It's quantum entanglement. There is no physical movement of information. It's just, well, if you know this about this aspect of this system, then you already know what the other aspect of the system is, simplistically. More technically, what it says is we get a weighted set for potential outcomes for some observable for this aspect of the system. What that's going to do is intrinsically give us a weighted set for other aspects of the system. If I change that weighted set for any of the aspects of the system, it will intrinsically change the weighted set of the occurrence of probabilities for the other systems as well. In short, measuring any one part of the system will intrinsically give you information about the other parts. The parts of the system are entangled to one another. But again, and I gotta stress this point, there is no physical transferal of information.
Ah,
That is not what entanglement says. That is not what happens in entanglement.
and that's key because even myself as a creationist, when I used to hear this, I used to say, "Wait a minute, doesn't that mean there can be a father and a son, and they're entangled, and there's two can be one, and we can have a Trinity's real. Quantum entanglement proves it." I used to say that,
Uh,
but it's. I'm glad you brought that up because we don't have. This is not. We're not talking about. There's no examples of people measuring some particle over here in the middle of the universe, and then another one over here in the other side of the universe, and they're like talking to each other and doing the same thing. That's not what it is. This
Yeah,
is
yeah.
so it leads to this. It leads me to this question: how do particles get entangled?
By interacting with each other generally. So if you have two photons that are emitted from the same source, you measure some observable for one of the photons. In the technical jargon, what you would say is the eigenstate for whatever observable you're measuring. Eigenstate just means the thing that got measured. That's really the state, the quantity that you measured for whatever particular observable or attribute observable of the system you're measuring. Position, momentum, spin, those are observables, things that you can measure, things that you can observe. What it's saying is that if you know the eigenstate for some observable of one photon, you'll know what the eigenstate for that same observable for the other photon will be, because they left from the same source. There was a point where they interacted with each other.
I
For
see.
instance, if you have an electron kind of just out in space, it's moving along, yada yada, it's doing something, all of a sudden it absorbs a photon and then re-emits it. If you measure that photon, if you measure some observable about that photon, it will intrinsically give you information, a weighted set of information about the observable corresponding to that electron, because they interacted. So now they are entangled.
And because of the laws of physics, that interaction would cause sort of a cause and effect on both of them
In a
going
sense,
forward.
yeah.
Yeah.
Much like with the baseballs, they interacted in that they collided and then started to move in other directions,
Sure.
which means that since they collided and that's what caused them to move in other directions, if you know the direction that one of them is moving in, you don't even have to measure the other one to know which direction it's moving in. The
Exactly.
reason that's the way it is because there was a point where they interacted, and that interaction, I'm trying to figure out the best way to put it, that interaction sort of, this is going to be a really bad way of putting it, but it's the only thing that comes to mind, sort of put in that information into the
Oh,
baseball such that you measure a quantity for one, you know what the quantity is for the other. Or weighted set is the more accurate term. I don't want to
yeah.
get beat up by the people that know more than me.
No, that made sense though. It made sense for someone like me because okay, so that brings me back. Let's bring us back to we're bringing this back to this sort of uncertainty principle and the double slit thing. And so but now that we've established how particles get entangled and what the whole misunderstanding is of this thing. So let's go back to this experiment. So what the camera, I should say, whatever the viewing mechanism is getting entangled with the photon. How?
By interacting with
So the
it. So if
photon from
you,
the camera actually hits the photon going into the slit?
it would be, if you were measuring a photon, I think you would use more like an electron. Photons don't, I think I'm correct when I say that photons don't really interact with each other, at least not in like the same sense that a photon and an electron interact with each other. That's probably why I should have used electrons instead of photons, because then the measuring device can shoot the photons at the electrons, and that's the only way. And that's essentially that's what we figured out with quantum mechanics, is if you want to measure a system, and it doesn't, this is another thing that I should probably qualify here, measurement or observer or observation does not mean consciousness. It means something that interacts with the system
Right.
such that it changes the evolution of that system in a somewhat of a simplistic sense. So that electron, before it goes to the slit, the photon comes off, it gets re-emitted by the electron. Well, now they're entangled. Well, because of that, that photon changes how that electron's going to evolve, such that it's just going to go through one of the slits instead of both of them, because the structure of its wave function looks different. Instead of being sort of looking like an interference pattern, it just looks like two humps corresponding to one of those two slits, rather than the multiple humps that start out, that kind of build up that hill, sort of representing an interference pattern. So
That-
when particles interact, they will change the structure of each other's wave functions, and thus change sort of the way that they evolve and the ways that we can describe them.
Wow, that's fascinating. So these particles, but they sort of operate like waves. Is that how it is when you get down to it? They're particles, but they operate like waves. Is that where the term waveable comes from?
In a sense, yes. A better way of putting it would be they're waves that sometimes act like particles, because particles aren't actually particles. They're always waves. We can just reduce their waviness, so to speak, such that we can make meaningful statements about them, at which point they start to look like or behave like a particle, a little bit of something.
So everything is basically waves in reality.
Yes, but not in the Deepak Chopra sense.
Right. I don't mean, yeah. But this is why I'm having this. This is why I'm doing this, because I'm so glad you brought that up, because you get people like Jordan Peterson and Deepak Chopra and myself, my past self, where we
My
don't,
past self as well.
yeah, we don't know what this stuff is, but we hear it. We watch the science channels and we hear it, and not having, and language is such a weird thing that we misinterpret things and then apply it to some sort of metaphysical worldview that we have, and all of a sudden we have scientific explanations for God,
Yep.
and that's why I wanted to talk about that, because that's what that's what it's all basically language, like the way we interpret things. And which brings me to the whole point of this video, is that we know now that, like, the Platonic worldview of metaphysics, forms, heaven and hell, there's no evidence for that. This was all just theories from the ancient world, but it was already contested early on by the Epicureans, the Stoics, who thought that everything was atoms and void. And basically what I'm getting at is, now in the modern world, Christianity's still huge, Islam's still huge. People still believe in this sort of perfect Platonic God. Like, for example, Nietzsche described Christianity as Platonism for the masses. He said, he basically said that Christianity, this label is because Christian obsession with the supreme God that Plato talked about, which is true. Augustine's Summum Bonum. This basically, if you read Timaeus, Plato talks about there's a first mover and he's perfect. And it's weird because Plato says he can't be jealous. What? That's weird. Christianity already falls
Kind of
apart.
granted that, didn't they? With the
Yes,
first, what is the first commandment or the second one? I am a jealous God. You shall have no other gods before me. Something like
yes.
that.
Yeah, so that right away we're already confused. But let's just ignore that part. Let's say they are talking about the Platonist God, because they do a lot of, like, Christian theologians and Catholic theologians. They'll say I'm a Neoplatonist. They'll say that. And so basically what I'm getting at is, for in order for this to be true, Platonism would have to be true. And we sort of gotten to a place now in our buildup of science, because science is always building off the past of people who come and they learn things and they add things to the conversation, and then someone else comes along and then you get people like Einstein who brings it all together, and you had these breakthroughs, and we get to a point now where we're on the backs of all these people, and we figured out a lot of things about the universe, about reality. And the Epicureans weren't right about everything, but they were right in the sense that this universe that we're in is atoms and void. So I say that to say this: wouldn't you agree that it's sort of a quick fix to kind of say, look, guys, Plato was wrong, and we don't have any evidence of metaphysics. In fact, it's the opposite.
So the one thing I do want to say is that some Christians would say that Platonism actually would be more detrimental to their view. William Lane Craig holds to this. He believes that if a Platonic realm exists, it's actually problematic for God. What's often referred to, I'm sure it's a term you've heard, God's divine aseity, that he exists in, of, and from himself alone. If there were a sort of a Platonistic realm and that's where numbers existed, well, then that would be separate from God. It wouldn't be in, of, and from himself. And so a lot of Christians will reject Platonism, but not necessarily all of them. I don't know how popular this view is. I know there's a lot
No,
of more of the sort of the type. I don't really know what philosophical terminology to refer specifically to Dr. Craig's total view, because it is quite a nuanced and technical view. But people who would there are many Christians who would agree with him that they would reject Platonism because they view that it threatens God's divine aseity. In
right.
terms of the philosophy, this is actually interesting. If I'm remembering correctly, I believe that Platonism, I think maybe Neoplatonism more, is actually not very. I don't actually think that it was behind nominalism in the 2020 Phil survey. I think that most of the responding philosophers were actually considered themselves some form of Platonist. But nominalism, I think, was like somewhere around 1% or 2, or maybe less than 1% behind it. Nominalism is the idea that like numbers don't exist in some non-material Platonistic realm, that they're just mere conceptions that don't
Right.
really have any ontology at all. And Dr. William Lane Craig is a nominalist. So a lot of Christians say, well, that's not respectable. And I say, well, a lot of popular Christian theologians like Dr. William Lane Craig are nominalists. So um,
No, what
what's that?
what you're getting at is exactly where I'm trying to examine and get to. Is just, and the reason, and I don't mean to cut you off, but what you're saying is the reason why I'm asking is doesn't that sort of make no sense then?
To me, a Platonist, even a Neoplatonist view, I'll just take Platonism to subsume Neoplatonism.
Yeah.
I have to be honest, I don't really understand that. But I'm not going to sit here and say that, like, I think it's wrong, but I'm not obviously going to sit and say, oh, it's stupid and dumb and you shouldn't believe. Not that you're saying that, because I don't think you are, or that you would, but I really struggle with this, with thinking that Platonism is true. What is the nature of this realm? How do we know that it's there? Well, simply because we have access to these ideas of numbers and these sort of previously understood as being Platonistic concepts. How do we know that these aren't just mere concepts alone with no real ontology at all? I mean, and I think that that's a little bit more of a simplistic view, personally, is to just say that, well, that there is no Platonistic realm. These are just concepts that exist in the minds of agents like humans. They don't really have an ontology. Numbers aren't a thing that exists. They're just ways that humans communicate the concept of quantity, which is a structure we observe that exists in reality. Now, that concept of quantity would exist in the sense that things come in quantities, but numbers are just a way that we use to represent that and communicate it. So for me, I really struggle with the idea of a Platonist view being true. It to me, it seems to add more than what we need to account for the things that we understand about the concepts that we use to understand and describe and communicate aspects of ourselves and the world that we exist within.
Yeah, and like, and that for some reason I remember you debated Darth Dawkins, and Darth Dawkins has this weird concept that he always likes to bring up, and he talks about the ultimate, which is in itself just a word. Like, you're
Yeah.
literally just saying a word. It's an abstract idea. We don't know. We don't have any, like, we can't look at it. We can't see it. We could talk about it. We could think about it. I could think of pink elephants flying in the sky. Doesn't mean they're there, but like, and so that's why I think Nietzsche was talking about Christianity being Platonism for the people, but because they're imagining this perfect being, and it's just an imagination. But then you get to what you said with William Lane Craig types who agree with all of us on basic science, basic, the universe is what it is, and the Big Bang happened, and the old Earth is real.
Oh, the Big Bang didn't just happen. It's evidence that God created the universe now. You got to remember that.
Right, and I'm going to get to that too. And he agrees about evolution. He agrees on everything that we're talking about, but somehow in the gaps, with everything we can't explain, like what happened before the Big Bang, for example, like you just said, had to be God. And but then I asked, what my question is, I want to hear what you think too. Where is he? Because if it's not a Platonist God, then doesn't that mean he has to be in the cloud somewhere? Like, doesn't he has to be somewhere, right?
I would agree with that. For me, I don't know. I'm not going to say something can't exist this way. I just don't know what it means to use the word existence. If you're describing something which exists, yet does not exist extended through space, does not exist extended through time, is not constituted of mass or energy. It's a quote that Aaron Raw, I remember he was in a debate with somebody, or a discussion like on his channel. He had brought somebody on the Why Do You Believe series, I think it's what it was. And the guy was talking about how God exists, but he's not in space. He's spaceless, timeless, immaterial, changeless, and then Aaron Raw was like, well, wait, then what is God? Like, look, if you're gonna say that there's something there, there has to be a there.
Right.
There. Like, you can't, otherwise, what is it? What is the referent of the words that you're using? What do your words describe? What is the thing they are describing, and how did you come to know that it possesses these properties? So when I hear, well, God exists, but he's spaceless, timeless, and immaterial, I just hear that God doesn't exist. I don't know what it means to say something exists and it's not in space. It's not, because think about it. If something actually doesn't exist, I think everybody could agree it will not exist in space, it will not exist in time, and it won't be constituted of mass or energy. It won't undergo change. So then, if that's also the same fundamental properties that things which are, say, supernatural possess, then what tools, what attributes, what characteristics can we use to differentiate between things which exist in that way and are supernatural, and those same things, but they just don't actually exist at all? How do we meaningfully differentiate between those two? And I don't think I think it's a very meaningful question. And I think that it is a serious hurdle for anyone, theist or not, that posits the existence of supernatural things. Is what's the difference between saying X exists and is supernatural and X does not exist? Give me a method that we can use to differentiate between those, because I have not seen one.
Such a good point. I've actually saw a post from somebody who said that some Neoplatonists now are saying that God exists in empty space. Well, then he's not there. And it's
Yeah,
like
it's like,
you just said,
what is he then? What
right.
is the thing that is extended through space? Is it some sort of energy, mass, which is energy? So, and if it is energy, how do we measure it? Is there a quantum field for it? Is there a particle associated with that field? I mean, we all talk about the God particle, and that was just the Higgs boson, but maybe there is a literal God particle, but we haven't seen that yet,
Right.
and it doesn't look like we're going to.
Yeah, and so this is why this is the predicament. It's like either he is this Platonist perfect first mover, and maybe in a deism sense, and then it's like then we have to we have to rethink all the science and all the philosophy that we're standing at right now, or like in the William Lane Craig sense, where is he? He has to exist somewhere, unless you want to say he's outside of the cosmic radio background and he's just like this gigantic force that's like watching us. And then and that's so ridiculous right there. And then it's like, then you get the whole God doesn't have a mind, he's perfect. But it's like, if he doesn't have a mind, then that cancels out Christianity, because the Christian God, he wants things, he has feelings, he gets jealous. That can't be the case either. So I say that all I say this. You got these deist arguments that are unfalsifiable, that all creationists hide behind and say, therefore, my book is true. You can't have it both ways. It's either one or the other. Either there is deism and he's outside of space and time and doesn't care about human. We have no evidence that he's actually really interacting with us. Fine, maybe that's the case. But it can't be that and he's interacting with us and he wants us to read his book. If that makes sense.
Yes, exactly. If at anything, whether it's some substance that makes us conscious, like a soul, or whether it's God or what have you, if it exists sans physical reality, sort of without, but and this is another thing that makes it hard. Terms like before, beyond, above, without, the universe, these, all those terms are spatio-temporal terms.
Right.
Once you're outside of that, they don't have any meaning. So the word is often sans, which is just, I think, the French word for without. If something exists sans physical reality, how does it interact with it? It would seem that, well, at the end of the day, you would have a violation of the conservation of energy. How
Exactly.
is it? How? And this is called what's known as the interaction problem. And theists really don't like it when you bring this objection up, because it's a that's one. I'm not even going to say that they struggle to overcome it, because they haven't overcome it. I don't know how what mechanism is being employed by this non-physical or non-natural entity such that causal effects occur in physical reality. I usually get, well, God's will. Well, sure, but a will is expressed on or through something.
Right.
So upon what or through what is God expressing his will such that causal changes occur in physical reality? These questions haven't been answered. It seems to me that the easiest answer, and I would say the one that Occam's razor would commit us to, is that such entities either A, just don't exist, which I would say is the simpler one, or B, they do exist, but there's no way we will ever, through any method, be able to observe, measure, detect, quantify, or understand what it is or how it works, at which point it becomes fundamentally indistinguishable, epistemically indistinguishable from just not existing at all. And so, in that sense, it's why even say that it does? Just shave it away with Occam's razor. We don't need to posit that it exists. If it does, there's nothing we're ever going to be able to do that shows that it does. And if it can interact with our reality, then we'll be able to measure it and quantify it. And in what sense is it non-physical?
Yeah, that was well put, and I have nothing to add. That was perfect. That was well put. But before we close out, anything you want to promote? Anything you want to plug before we go?
Um, Other than my channel, I don't post content super regularly just because with some of the stuff that I do, I don't do like a weekly show or something. I've thought about starting like a political one, but I want to get some more stuff figured out, and I'm just waiting for the opportune moment with finances and stuff to really get there. So that might start. But I do post content on my channel. I can be found on a lot of other streams. GR streams, GRR, and then streams, two separate words. Does a lot of streams. Answers in Atheism, all one word. Streams Mondays, Wednesdays, and Fridays. He does a weather report. He goes over a lot of the, pardon my French, the creationist bullshit that's happened, throughout the week, and he covers it. It's a good program. I post not regularly, maybe once every 2 to 4 weeks. It just depends on what's out there. I'm getting ready to start writing a script for a response to a video, Standing for Truth. That he's a very prominent young Earth creationist here on YouTube. He did a response to a video featuring our wonderful Erica Gutsick Gibbon with Seth Andrews, I believe,
Yes.
talking about the distant starlight problem. I'm not going to explain what that is. If you want to learn more, you'll just have to subscribe to my channel and look for that video, where I will be responding to his response, which is a reiteration, a clip. I think it's a couple of clips from a video he did, I think about a year or so ago, where he had PhD astrophysicist Jason Lyle. No, I don't. On his channel, who is also a young Earth creationist and posits what he calls the anisotropic synchrony convention to overcome the distant starlight problem, which distant starlight, billions of years, Earth is on the whole universe is only 6,000 years old. There's an obvious antagonism between those two ideas. That's the distant starlight problem. And I'm going to be doing a response to that because
That's going to be gold.
boy, it's bad. And there's actually, well, I guess technically it is a fallacy that the anisotropic synchrony convention argument commits, and I'm not going to reveal that here. But feel free to subscribe to my channel. You don't have to. Like I said, I am a content creator, but I don't do anything regularly. I'm hoping that by the middle of summer, I'm starting to post a little bit more regularly. But I like to do a lot of the debate reviews, response style content. So it's sort of as the content I want to respond to comes out, then I put out the content. Answers in Atheism, another really good channel you should subscribe to. There was another Amy Newman. Don't know if you guys know her. She's really good to subscribe to. And these are just channels that I frequent in my free time, and I think that they put out a lot of really good content. And one more channel I would like to plug. They go by PSF on YouTube. It's the Promethean Secular Frontier, but they just go by the letters PSF. They do, in my opinion, that is one of the most underrated channels I've ever seen. If you can go check them out, you need to do it. They host the most amazing discussions. They just had Ethan Siegel on last night talking about dark matter and dark energy. He has his PhD in theoretical astrophysics. He's a science communicator. He's won numerous prestigious awards for his communication. And if you watch the videos where they have him on, you'll see why. I was supposed to be on that video yesterday, but because I'm an idiot and I had it in the calendar on my phone set to the 28th, next Monday, instead of the 21st, yesterday, because, sometimes you misclick when the stuff on your screen is small. And so I'm really mad at myself for missing the opportunity to be on a stream with them talking about my favorite subject, cosmology. But I'm hoping I'll get another opportunity. So that's another channel you guys should really, really go check out if you like more of the secular atheist content. They do science, they do philosophy, they do feminism, a little bit of, liberalism, leftism. And I know that's not for everybody, but
Sure.
sometimes just getting different perspectives
Yeah.
is a good thing. But yeah, check us all out. We're trying to be a part of the community and put out the content that keeps people thinking.
That's awesome. And by the way, you need to. I really hope that you do start posting more because you're a very smart, articulate guy, and the conversation for truth needs you. So I really hope you do. And by the way, are you going for a PhD in anything or?
I am not. In fact, I have no degrees in anything from any accredited
Wow.
universities. I
That's mind blowing.
fucking love physics is about the best way I can put it.
That's actually more.
And
That's actually
what's
more
that?
impressive that you know all this and you're just self-taught.
I can say that Sean Carroll's The Biggest Ideas in the Universe, which he has on his YouTube channel, just Sean Carroll. Such a phenomenal series. He is my favorite. So he is my number one. Not really idol. What's the word I'm looking for?
Role model.
Role model, influence in physics, because he understands physics at a level beyond what I think probably any human will ever understand it, for at least since maybe Feynman, and probably God knows how long it's going to be. I mean, he really is that good. He understands the philosophy and his way of communicating it. It's like Ethan Siegel. He just knows how to talk. He just knows what to say and how to put the idea in a way that people are going to understand it.
Yeah.
MIT OpenCourseWare, Leonard Susskind, one of the world's most renowned theoretical physicists, has a lecture series through Stanford University called The Theoretical Minimum. I mean, he touches on everything: classical mechanics, quantum mechanics, advanced quantum mechanics, special relativity, cosmology, general relativity. So I've done that. Brilliant.org, Khan Academy, The Great Courses, or Wondrium, which is more of a subscription thing they have.
Yep.
All of these are resources that I've used. The resources to learn these things are out there. I get a lot of people say, how do you know this stuff and you don't have a degree? The resources are out there. You just got to use them. And I encourage people, use them.
See behind me, that's all those,
yes,
those are all history, all ancient history books, all of it. That's my thing. I love it. Like
and reading.
I can't lay down at night and go to sleep without a book in my hand. I'll literally start pacing and racing. I have to literally open up a book. Doesn't matter what it is, but Josephus, Philo, Pliny the Elder, whoever. I'll just pick one of them up and just start reading it. Start reading about the ancient Romans and the ancient Greeks. Fall asleep within a half an hour, 45 minutes.
And books are out there. And one that I always get asked about is quantum mechanics. What's the best way to start learning that? I always tell people, brush up on math. You don't need to be a mathematician, but having a basic, at least conceptual understanding of single variable calculus, differentiation, integration, and then linear algebra, you'll be just fine. And this book, which is actually by Leonard Susskind, it's based off of the lecture series he did through Stanford University. Quantum Mechanics, The Theoretical Minimum. I've actually read this twice, and I do plan on reading it again, just because you can't ever learn too much about something, and if you think you can, you probably don't know that much about it to begin with.
Nice.
This, I would say, is one of the greatest books for learning about specifically this subject, if it's something you want to learn. Get up to speed on your math if you're not, because I know some people out there that aren't. I was one of those people back in high school. I didn't care about math. I do now. Wonderful book. He's got another one on classical mechanics and another one on special relativity and classical field theory. Reading books is, like you alluded to, is obviously a great way to learn. The resources are out there. Get out there, use them, learn it, apply it, change the world.
Yeah, man. And I hope everybody was taking notes on all those resources, because you guys can do the same thing. And like I always say, you have just attained true gnosis.
You have just attained true gnosis. The demiurge has no power over you.